Okay, so an empirical formula is the smallest whole number ratio of elements in a compound. And so when we're looking at empirical formulas, we might not be dealing with ionic compounds specifically, but what I want you to think about is these are the reduced versions, okay? The very, very most reduced versions, similar to the way we use ionic compounds, okay? So an empirical formula, let's say if I give you two options, you're going to tell me which of these is the empirical formula and which is not. Okay, so if I give you, which of those is the empirical formula? The second one, right? The one on the right. These two both have the same ratio of carbon atoms to hydrogen atoms, but one of them is all the way reduced. So this would be what we consider the empirical formula, okay? And this is what we call the molecular formula, and we'll talk about that next class, okay? But essentially, the most reduced version that we can have is called the empirical formula. And so that's what we're going to look at today, okay? In an ionic compound, an ionic formula is always an empirical formula because it's always the most reduced version. In a covalent compound, it's not necessarily the case, right? In a covalent compound, we could have both this and this, which mean totally different things, right? They behave differently, they have different properties, but they just happen to have the same ratio of elements. In ionic compounds, it's always the empirical formula. In covalent compounds, you can have both empirical and molecular. Okay, does that kind of make sense or not so much? A little bit? Okay, today we're going to learn how to take an unknown compound and create its empirical formula based on the ratios of each element to one another. Okay, that's what we're going to do today. We're going to go from an unknown sample of a substance to giving its empirical formula. Okay? So, the way we kind of segue from yesterday's lesson into today's is that most of the time our empirical formula problems start with a percent composition. Okay, so most of the time they start with a percent composition. So this is kind of our steps for finding an empirical formula. Okay, so we need to start with a percent composition. And this would be something like, this sample has 30% carbon and 70% oxygen, right? And we would be able to go from there to look at the ratios. But essentially we need to start with a percent composition. Okay, or the number of grams of each element. Okay, if we're given the number of grams to start our problem, that saves us one step. So we can either start with a percent composition or the number of grams, whichever of those is given to us. Okay? When we have a percent composition, what should the percentages add up to? When we have percent composition, what should they add up to? 100, right? All the percentages of each element should add up to 100%. So when we're looking at the ratios of these elements from one to the other, we're going to act like if we're given a percent to start, okay, let's say that this is the case. Now let's say if we're given a percent composition to start, we're going to act like we're just dealing with 100 grams of our substance. And we're going to turn each of those percentages just into grams. Okay, so you're going to say, step 2 kind of here would be turn percentage to grams. And that's really as simple as saying if it's 70% carbon, then you just say, okay, now I'm going to say we're dealing with 70 grams of carbon. That's it, right? We're just going to assume we're using 100 grams of our sample. So if we had 30% hydrogen, which this is not a real compound, I'm just making this up, we would be saying, okay, we're going to use 30 grams of hydrogen. Okay, does that make sense? That's all we're doing in our first step. So if we were given grams to start, right, we don't have to do this part of our problem. If we're given grams as our starting amount, we take that whole first step out. Okay, so if we start with a percent composition, we just flip it to grams right away. If we started with grams, if our question gives us grams to begin with, we don't have to do that. Okay, does that make sense? Okay, so now we've got that our starting amounts are ready to go. Okay, remember this example I gave you is made up, so that's not a real thing. Okay, We're just showing how we go from percentage to grams. So now our next step, once everything is in grams, right? Once all of our values are in grams, we are going to, let's say this is step 3, we're going to convert grams to moles of each element. Okay, we're going to convert grams to moles of each element. So why do you think this might be important to convert from grams to moles?
This is the simplest.
Okay, kind of the simplest. What do you mean by the simplest? Can you expand on that a little bit more?
Like the most reduced.
Okay, kind of. What's the easiest way to compare two elements? In grams or in moles? In moles. It's really hard to compare the amount of an element if we look at grams, right? Because 1 gram of hydrogen is 1 mole. But 1 gram of iron is, like 5% of a mole. Does that make sense? So the values of these elements are very different based on whether we're comparing them in grams or moles. Okay, so moles is the only real quantity that we can compare to values and they be all equal, right? We want to compare them in moles. So we're going to convert them each to moles so that we can see what is our ratio, okay? So once we have them in moles, we will divide each number, I'm going to actually say each amount. Each amount of moles by the smallest value. So what this does for us, this step right here, step 4, allows us to see our ratio of elements. Okay, it allows us to see the ratio of elements. Okay, so for example, let's say if I was dealing with 0.2 moles of hydrogen and 0.4 moles of oxygen, right? I would divide each of those by the smallest, and I would say 1 hydrogen atom to every 2 oxygen atoms. Right? It shows us the ratio, or how many of each of these we need in comparison to the other. Okay, so hopefully these steps will start making sense a little bit more when we walk through a problem, but I'm going to give you all the steps first. Okay, once we have our ratio of elements, all we have to do is put our compound together. So last step 5, is build your compound. Okay, so step 5 is build compound. Okay, and if we're looking at our questions, we're most of the time going to go in the order that they were given. Okay, so now that you have all of these steps, we're going to do some practice. So you can turn to that practice handout that I gave you. Make sure you're on the side that says Empirical Formula. All right. So we're going to look at following these steps all the way through. So our overall goal is to find the empirical formula of some sample that contains 89.14% AU, which what is AU?
Atomic mass.
No. AU is an element. It's gold. Okay, and 10.8% of oxygen. Okay, so we can't just build a compound based on percentages because it has to do with their mole ratio, right? How much each weighs and all that kind of stuff. So first step is to take each percent and turn it into what? Grams. Okay, so I'm going to start building them over here. 89.14 grams of AU. And then I'm going to convert to moles. So I'm just going to build my little mini T-chart right there. Okay, my second element is oxygen. So I'm going to come down here and I'm going to say I have 10.80 grams of oxygen. Okay, and I'll start my T-chart there. So I've converted each of them to grams, right? That's as simple as it gets. All I'm taking is from percent to grams. Now to go from grams to moles, how do we go about doing that? right? I have to use the atomic mass or the molar mass. So if I want to go from grams to moles, grams needs to go on the bottom, and moles always gets the what? The 1. So what number goes here? The molar mass, right? So the molar mass of gold is what? 196.96, so yeah, I'll round up to 197. Okay? Does everyone understand how we're converting from grams to moles? Do we feel really comfortable with that? We should by this point, okay? So grams of AU and moles of AU. Let's go ahead and calculate that out. All right, I'm done with grams. I'm left with moles. I want to multiply across the whole top, divide by the whole bottom. So 89.14 divided by 197. Okay, and that gives us 0.452 moles. With this step right here, putting our number of moles, you don't want to round too early, because if we round too early, if we would have just rounded this to 0.4 or to 0.5, it can throw off our ratios a little bit. So for this number, I want you to keep 2 or 3 decimal places, okay? Because we want to be as exact as we can in terms of our ratios, okay? So to go from grams to moles of oxygen, we're going to do the same process. So grams of oxygen to moles of oxygen. Moles gets the 1. And what's the molar mass of oxygen? 16. Good. Okay, so our units cancel like they should. So we'll do 10.8 divided by 16. And we get 0.675 moles. Okay. We want to divide by the smallest amount now, so we'll divide both of those values by 0.452. Okay, that means we should have 1 gold atom, right? Whenever we do this step, there should always be a value that comes out to 1, because you should be dividing one of them by itself, right? Here we're going to divide by 0.452. And we get what? 1.49, right? Or 1.5 oxygen. So here's something that we need to think about. As we go to build our compound, can we have AuO 1.5? Do we ever see things with fractions here or decimals? No. So what do you think the solution might be to that? Multiply by 2. Right? Get this to a whole number. So to get 1.5 to a whole number, we have to multiply by 2. And if we do it for oxygen, we have to do it for gold as well. Okay? Because the ratio is 1.5 to 1. So what we're going to do is we're going to take this whole compound multiplied by 2, and we get AU2O3. Right, having this fraction right here, we try to avoid ones like that, but when they come up, they should be pretty clear as to what you would need to multiply it by, right? You're not going to get a 1.7 something there. That would be hard to tell, right? It should be pretty clear if you need to double that or even triple that. That would allow you to do that.
So you just multiply it until it gets to
until you get it to a whole number. And then whatever you had to multiply that by, you have to multiply the other one by. Okay? Good question. Any other questions for that process? When we go to build our compound, it's when in doubt, we're just going to build it in the order given. So they gave gold first. Gold needs to go first in our compound. Oxygen needs to come second, right? It also follows our rules of left to right on the periodic table. Okay, so if when in doubt, go with what's given, but usually we're working left to right on the periodic table. Okay? Questions there? These problems take a little bit of math, right? A little bit of step by step, but the algebra behind it is not difficult, and each problem is solved the same way. So if you can get the process down, you'll be good to go. Okay? Let's try the second one. Okay, so this talks about now nitrogen and hydrogen and sulfur and oxygen. So we've got 4 different elements going in here. Okay? The good news is the process is exactly the same. The bad news is you just have a little bit more math to do. Okay? So we're starting in percents. What do we need to do first off?
Grams.
Go to grams. So I'm going to set all of mine up here over on the side. 21.2 grams of nitrogen. 6.1 grams of hydrogen. Okay, and we're going to convert each of those to moles. So for all of those, all we're doing is dividing by their molar mass. Okay, so grams of nitrogen needs to go on the bottom. So go ahead and work however fast or slow you need to here. Just check the board if you have questions. Sulfur and nitrogen and oxygen are all close enough to a whole number, right? All four of these are close enough to whole number molar masses that I'm okay with rounding to a whole number. If you prefer to carry a decimal place, that's fine. Remember, when you're looking at the number of moles, you want to probably keep a few decimal places there. Okay. A lot of you will want to stop at this point and try to build your compound. Okay, it's not how it goes. You have to divide by the smallest number. Otherwise, you're not seeing the ratio that you need to see. Okay, right now this is just about the number of moles. This is a quantity. We want to find the ratio of these. Okay, so which is our smallest amount of moles? Right, sulfur. So we're going to take each of those divided by 0.755. Were these the numbers that you guys were coming out with? Do they match yours? Okay. Do we agree? Your numbers, once you get to this part right here, should be coming out to whole numbers, right? Or really, really close to whole numbers. If they don't, that's when we might have to do that multiplication step to get us to a whole number. Okay? Did you have a question? What's different about this one than the ones we've seen previous?
It gives you the grams already.
It already gives us grams, right? So it just takes out the first step for us. It tells us the total weighs 140. We don't really need to do anything with that 140, right? If you want to make sure that these add up to 140, that's fine. It might say that, it contains this much, and the remaining is oxygen, in which case you would take 140 minus that. But in this problem, it gave you everything that you need. So you don't need that 140 to go into part of your problem at all. But we're just going to take exactly what was given to us. Anybody name that molecule for me?
Nitric acid.
Good, nitric acid. Right, this is nitrate by itself with a hydrogen in the front. Good. Between these two, right, they were both very similar. Did it really matter which one we divided between? No, it really didn't matter which one we picked, right? You always pick the smaller one, yes, but essentially they were still a 1-to-1 ratio. So, any questions on that? Did everybody get that to come out okay? Okay, very good.